The great switcheroo. Yeah. That's nice.
I like that.
Yeah, that's well done.
I think that gets the point home immediately, doesn't it? You know, for even if you don't look into any of the mathematics, at least you know immediately what we're talking about, right?
Have you heard, Gav and I've talked about it a few times, where we talk about how they had the great switcheroo, which is where they switched us from realizing that we looked at a Euclidean world through spherical eyes into believing that we look at a spherical world through Euclidean eyes. They flipped it right around.
Yeah, I think, well, according to history, I think it was the Greeks who did that. That's how, the history we're told at least.
Yeah, we think it's a bit late. We think it was Gauss and Riemann.
Yep.
A lot more recent.
I'm pretty sure it was around about those times as well, yeah. At least formally, the way they've done it. I mean, for me, the mathematics works the same. If you're on a round ball and you tell everybody that they have planar vision, i.e. what they would normally call perspective representation, then the geometry of everything that you see and all the appearances is the same as if you were on a flat plane, but you had globular vision, spherical vision. So spherical vision on a flat plane is the same as planar vision on a spherical surface. So it's just switched round, if you like, yeah. And, you know, I think the person who discovered it was a guy called Thomas Reid, who you probably heard me talking about. He was a polymath in Scotland, who was the first person to write about the geometry of visibles. And the first, or probably one of the first to make the distinction between tangible geometry and visible geometry. And he wrote quite well, not quite extensively, he did some experiments, which I think are great, and wrote about it, and basically defined 10 or 12 axioms without going through any of the further mathematics. And it's exactly the same axioms that Riemann used 70 years later to define his, you know, or what Gauss and Riemann both used to define the curvature of the Earth, and the valid mathematical geometry that we have now that Einstein went on to use, and, you know, all the bullshit. So this guy, I think, about 70 years before Riemann, so about 1750, was the first guy to really, you know, dive into it in any detail. And I'm pretty sure that he got sidelined and sidetracked, and the people saw what he'd done and reused his mathematics to make the deception work properly. I'm not saying there wasn't deception before that, you know, I'm pretty sure there was, but I think that was the big turning point, at least as far as I can research.
Well, I know they started.
Sorry, go ahead.
No, go ahead.
I was just going to say, I think that's where they basically came into this whole paradigm now where they've got mathematical proofs for everything.
I think the eye works, and why it's correct to use the circular arc, because our eye is globular and the back of the retina is a curved surface, so that what's happening at the back of my eye in my retina can be represented by an arc in front of my eye, which is why I've set up these geometric diagrams that way. And then there's basically, you know, the planar angle that you need, and there's basically only two theorems that you need to know to understand direct vision. And direct vision, the theory of direct vision, I think, is different from the theory of perspective. Perspective for me is representing 3D objects on a 2D planar surface by mathematical rules, whereas the theory of direct vision is applied to how your eye works. It's, you know, geometrical optics rather than paintings or drawings, yeah, or technical drawings. And there's only two theorems that you really need to know, and that is that objects have that proportion respectively as the angles under which they are seen. And I've got geometrical proofs in here, right? So I went through all the diagrams, did all the proofs, and also show in here, you know, certain things that people take for granted, but they shouldn't take for granted. So things, it's not as simple as saying, if something's twice as far away, then it's going to be half the size. You know, that's what ballers tell us, right?
Yeah.
But it's actually a lot more complicated than that, depending on the situation of your eye and how the object is. Yeah. Maybe if I just run briefly, at least before we dive into any more detail about a little bit the history of how I got to it, right? You know, I think the major thing was this differentiation between visibles and tangibles. And I don't know if you guys have heard me saying this on Dell's before, but the very fact that we do not attend to visible figure is one of the biggest problems that we have as humans, right? When I say we don't attend to visible figure, what I mean is, if I ask you now what the shape of the table is in front of you, Zach, what shape is the table?
Which shape?
Any table. Any table, yeah.
I mean, it's a rectangle. I don't know. What was...
That's the tangible shape, right?
Yeah.
That you, when I ask that question, you will automatically jump to answering it and saying, yeah, that table is rectangular, right? But if you look at it and you look at its visible figure, it's not a rectangle, right?
No, it's kind of...
It's a trapeze or a parallelogram or...
Yeah, you know, one of those. Yeah, exactly.
And wherever you walk in the room, that visible figure is going to change, right? So that, yes, the tangible object, the physical object is a rectangular shape that doesn't change because it's substantial, but the visible figure will depend, whatever, on where you are in the room in relation to the object and what angle you're viewing from it. So that table is always changing shape, right? But you will never attend to that. You know, you will not direct your attention, or what the philosophers call today intentionality, which is a word I fucking hate, but you will not direct your attention to it in such a way that you actually see what you're actually seeing, what your eyes are seeing. You're jumping immediately to what you know it represents in your head. As Reed said, you don't see the signs, you automatically go to the things signified by them. And that was, for me, a major kind of clue and understanding that, yes, we look at things all the time, but we actually don't see its visible shape and extension. Right? And that there is a real differentiation between tangible objects and visible objects, which at the end of the day, we shorten down to tangibles and visibles, right? So a visible object is something that we can contemplate, we can study, we can mathematically look at, we can all experience and observe them if we direct our attention to it. Yes, so it is an object of thought. The same way a physical object is also something that we can think about, build, construct, right? And that these two things are separate things and they need to be treated separately. And that the tangible object is very much Euclidean planar geometry. That's what the whole world is constructed on, levels and perpendiculars and parallels. But visible object is not. It actually obeys the rules of spherical geometry. Now, you might, or we'll all find that in the first instance a little bit tricky to understand, because you'll say, but I don't see things curved, Gavin, right? And the explanation of that is that if you're at the center of that sphere looking out, then of course you will not see the outward curves of the sphere. So when you're looking at something, you'll see it as a straight line. But that doesn't mean that the geometry of visual perception is not spherical. Just because it looks Euclidean, it's not. It's actually spherical, right? And because we direct our attention to things, we're always looking straight on at stuff, and it appears to be Euclidean because you will never see the outward curve of your own eye, right? You will always see the same way that if I, put something like this, it looks like a line, right? And you don't see that it's a plane, right? It's a similar problem, yeah? So we don't attend to visible figure, and we don't realize that it's spherical in nature and not planar the way they tell it is, because they confuse the definitions of perspective, and they have us looking at flat screens all our life, and so we tend to think everything's just planar. So that's the first thing, that I think that differentiation between visibles and tangibles was a key eye-opener for me. And another question that kind of fortifies what I'm saying, if I ask you, have you ever experienced double vision?
Yes.
When you were drunk or when you knocked your head?
When I was drunk a couple times, but my eyes, if I'm thinking about something really intensely and my mind starts to wander, I'll notice when I come back that my eyes are kind of crossed and I'm seeing two of everything.
Yeah.
So yeah,
Now,
it happens to me quite a bit.
If I was to ask you to put your finger out in front of your hand, out in front of your eyes, and look at your finger and attend to what's behind your finger, tell me how many heads you see of me.
Wow, yeah.
And if you look at my head,
I see two of my fingers.
Yeah, if you look at my head, you'll see two of my fingers. So the actual reality of the thing is we see double all the time. We just don't attend to it. We throw away that piece of information, if you like, so that what the eye is actually doing at any one given instant is a lot more different than we think it's doing, because we jump automatically to the things that we think are signified by them, and we don't actually see the visible signs, right? So that's kind of like two examples of you know, when you realize that there is a real difference, then you can actually start to study them as different. But if you don't even make that distinction, which mathematicians don't do either, then you don't get anywhere looking at where the problem might lie, right?
I never thought of it that way. Yeah, that's...
Yeah, well put, extremely well put.
Very well put, yeah.
Except for the fact that if you didn't do it that way, you'd be falling over and tripping over things all the time.
Exactly. I mean, it kind of gets back to this, you know, and I don't like whatever this, you know, let's leave the creator out of this. And I'd prefer to call it nature, but it's just one of these things that nature gives us that is, how should I say, true. It's not self-evidently true because we don't attend to it. We don't direct our attention to it, but it's just something that's given to us, right? We come to the world this way and it's the way it is, but nobody's really completely understood it.
We've probably discussed this before, but I don't know. I'm sort of going through this. What's going through my head at the moment is like I just said. It's part of our constitution not to attend to it.
Yes, I agree because to cross the road, we have to think that the car is coming towards us. We don't sit and look and see the visible figure of the car changing as it's coming towards us. We jump immediately to get out the fucking way or you're going to be hit, right? So yes, it's necessary for our survival, I think. Yeah, is what you're saying, right? Yeah.
It's sort of like, okay, they've played on that. The powers that be have played on the fact that our constitution puts that out of our mind.
Yep.
And they make sure it stays out of our mind. Because if you come back and do attend to it, you can work out what's going on. Whereas in day-to-day living, you're best not to attend to those things.
Yep. Yep. Absolutely. Yeah, and I think the next thing that for me was important to understand was the planar and spherical geometry. So if I draw, you know, two lines here on a plane, then the mathematical relationship, if this was a triangle, that these angles all add up to 180 degrees, will not change irrespective of where I put this plane in any direction. The properties of that triangle will never change. A plane is a plane in any situation, in any orientation, inclination, it doesn't matter. The properties of something on a plane never change, irrespective of its orientation in 3D space, right? Those angles will never change. But that is not the case for a sphere. There's no such concept, for example, of similar triangles. So I think you guys all know what a similar triangle is, right? If I'm drawing this very hurriedly and badly, but a similar triangle is that if I scale it up, then it's always still going to be 180 degrees, and the proportion of the sides to each other or the angles to each other is always going to stay in the same relation.
Yeah.
And that doesn't matter how big my plane is. But that's not the case in a sphere. If I draw a little triangle on a balloon and I blow up the balloon, then the angles of that spherical triangle on that balloon are going to get bigger and bigger. They can go all the way up to 720 degrees, right? On a sphere. And if any two triangles are, well, there's no concept of similarity, there's only congruity. So if a spherical triangle has the same angle size, then it's the same triangle. It's not like a plane where it could be a small one or a big one or a, yeah, it only is that one spherical triangle, and it has to be on a certain size on a sphere to be that triangle. There is no such concept of similarity on a sphere, yeah? The same way that I showed it as a plane. So that, and one key concept in mathematics is also the difference between a sphere and a ball. To qualify that in geometry, a sphere is only the surface of the sphere and not the substance inside the sphere. Whereas a ball is the surface and all the stuff in between. But I call it a two-sphere and a three-ball because a sphere is a two-dimensional object embedded in a three-dimensional space that you're supposed to believe is possible. Whereas a three-ball is a three-dimensional ball, like a bowling ball, or what they tell us the Earth is in a vacuum. But a two-sphere, or any sphere, a mathematical sphere, when they talk about spheres, it's a two-dimensional object, which is only talking about the surface of the object. And you're supposed to imagine, as a mathematician, that that is possible, that you can have a curved surface, but you don't need to worry about the space that it's curving into. Right? You're mathematically looking at that object as a two-dimensional surface and the properties of that surface, but don't worry about the fact that in reality it would need to curve into something. That it gets thrown out the window in spherical mathematics, yeah? Now it's a powerful concept to use for a lot of different applications. For example, in navigation, right? Where things then simplify when you can use spherical triangles to basically find out where you are, because an observation of the stars and somewhere on Earth, a flat plane, you can basically reduce your problem to finding out where you are on this flat plane by solving an astronomical spherical triangle at a given instant in time. So that's why it was very powerful in the old days in navigation when they were talking about the celestial sphere. And it's also powerful in a lot of other ways. So, you know, mathematically, it is an object that, yes, you can think about and it's useful. But what they like to do is confuse the sphere, the two-sphere, and the three-ball. So a layman will not understand that difference. And anything that they say about spherical mathematics, they automatically assume means a three-dimensional ball. So that's also a very important distinction, right? I think we've did a couple of videos on that, Glenn, as well.
Hold on
Yeah,
one
we
second.
probably should go through and pull out the bits and pieces of those videos so that Chris and Zach can have a look at them.
Yeah.
Actually, I'll do that. I'll go through and I'll edit them a bit.
That's fine.
Yeah, I don't know. Do you have them at hand at the moment? If you think there's something we should show immediately?
I haven't got them at hand at the moment, actually. I've just got our hangouts, but I wouldn't know which ones to go to.
No, okay.
No, probably better off doing it the way you're doing it at the moment. I can see that the boys are gobsmacked. So
yeah, it makes so much sense.
So let me just to go into that slightly in more detail. I don't want to detract from what we're saying, but it is an important distinction. Let me share my screen. This one. So can you guys see that?
Yep.
Yeah.
So this is a sphere or a ball, right? Because both the representations of both of these things would be the same. right? There's no way to visually show a sphere that doesn't look like a ball, right? And if I show you a ball, it's going to be exactly the same as showing you a mathematical sphere, even though one mathematically is treated as two-dimensional and the other one's a three-dimensional ball, right? There's no way to do it. I wouldn't know how. And they know that, right? So, but just to make it very clear, so a sphere is always only concerned about the surface and never about the points in the middle. There is no center, if you like, to a sphere. It doesn't, or put it this way, it doesn't belong to the sphere, right? It's only the surface that counts. And the way they measure the radius or the diameter of a sphere is you have to stay on the surface. With a ball, you can go right through the middle and say, that's the diameter of the sphere. But on a the diameter of a ball. But on a mathematical sphere, you can't go through the middle because the middle doesn't belong to the sphere and it's not on the surface. So they define, mathematicians define the diameter as going from one point on the equatorial circle up over the North Pole and down the other side. That is the definition of a diameter on a sphere, and not what you would intuitively think to go right through the middle of the ball, because you're not allowed to.
I did not know that.
It also has one implication that's quite interesting. Do you think pi is a constant?
That's what they tell us, but
In planar geometry, it is, right? In planar geometry, if I draw a circle on, if I draw a circle here, then it doesn't matter what size that circle will be, the ratio of the circumference to the diameter will always be pi. That's the definition of pi, the ratio of the length of the circumference to the length of a diameter is pi. But if you go back to the sphere here, then you will see that it's not the case, because what I've drawn here is one diameter of this sphere, and you can see that that's half of a great circle. A great circle would go all the way around and back round to the bottom again, which means that the circumference divided by the diameter here is 2.
Yeah.
So pi is not a constant in spherical geometry. It's only a constant in planar geometry.
Wow.
So one of sorry?
It's mind blowing.
Yeah. Why I can't believe they didn't teach me that in geometry.
They like to keep these things away. I think I actually mentioned it here. Yeah. So you can. This is where it says here. Yeah. Yeah. So for different circles of latitude, your spherical pi will change. So for example, if I take this circle up here, right, this latitude circle, and I want to know the diameter of that circle, then the diameter is from the point K up over the North Pole down to J, right? That is the diameter of that circle of latitude on the sphere. And that works out to have an even different, you know, in this case, it's 2.84, right?
So it's constantly changing, always.
It's constantly changing, yes. It's constantly changing depending on your circle of latitude. Pi constantly changes on a sphere.
Oh,
something that is very relevant to the measurements that get made, right?
Yeah, huge.
Okay. The other thing that, you know, I thought was important. So that's that distinction, making sure that a 2-sphere and a 3-ball are not allowed to be confused, and that mathematically there's a different way of manipulating the properties of a sphere that there is to a ball. But, and this is the important point, they also have many, many, many similarities, which you can see as kind of obvious, right? Not only can I not just represent them the same way, they always look the same, but they also share many geometrical properties, because the surface, if you like, is part of the ball. Yeah, it's just that we're not allowed to talk about the center point on a sphere. But we do want to talk about the center point, because if we're talking about the eye, then it's highly relevant, yeah? So you can see that these two things have very, very many properties in common, which makes it easy for them to jump between the two without anybody noticing it, including mathematicians. But there are certain things that are, yeah, that you can't just assume. And that's where they play on the sophistry, if you ask me. Yeah, so that was an important point. I think the third important point, I think, is this. I actually had one video. So this idea that, so I want to, when we look at these diagrams later on, or if we go through the document, and I introduce this arc as the way of measuring the angles, then I want to have a justification why I'm using that arc, yeah? And the justification is not just rooted in the fact that my eyeball is a sphere. That might be enough for some people, right? And it's fairly intuitively good. I think that that's a kind of common sense thing that, yes, you know, most people will agree on. But mathematically, there's also a very important point that because of these similarities between a sphere and a ball, the angle subtended, I need to do let me find 2 pens, it might be better. So the angle subtended at the eye, when I look at something, this is what they call a planar angle. If I put this back onto a plane, then that planar angle will not change any way I do things again, right? The planar angle stays the same. But the solid angle, so if I now have 2 planes, if I have 2 planes meeting each other, then the angle in between these 2 planes is what they call the solid angle, right? So a planar angle, the one that I just drew with or the one that I was doing here with my 2 pens, sorry, my props are not very good today, but with my 2 pens, and the 2 planes coming together are basically the same angle. And because that holds true geometrically, it means that the angle measured at the center of the sphere or the ball can be measured, that angle, if I extend that out into a sphere, then that angle can be measured by the magnitude of this arc segment on the surface of a sphere. So if I was to make this angle bigger, how do I do this here, bigger or smaller, then the arc segment on a sphere is the measure of that internal angle at the center. Now that's a mathematical fact. I've also got a little proof of that for people who want to dive in more deeply. But basically, there's a justification for me saying, okay, this angle subtended at the eye, we can measure it according to the length of the arc segment on a sphere, and the sphere can be any size because the arc segment is always going to be a measure of that angle. The further out I go, it doesn't matter. In relation to the total degrees of 360, that arc segment length is always going to be proportional to whatever angle I'm measuring as well, right? So yep. Geometrically, because a planar angle and a solid angle subtended at the center are equivalent, and because from Euclidean geometry about balls, you know, like a real solid ball, if you cut a melon, you know, and let's say you take a cutout of a melon, right? Or an apple or whatever, then the measure of that solid angle is the gap that you've left on the surface of that watermelon, right? It's a known fact. And it also works, it also holds with the sphere.
It's representational, isn't it? It's like they're proportional representations. One's an angular proportion and one's an arc segment proportion.
Yeah.
It's going to be the arc length is going to be a proportion of the circumference, and it's always going to be equal to that same angular proportion.
That's right. And in astronomy, they call it angular distance, right? Or angular size. You know, they like to confuse the terms and terminology of what it actually is. But that's basically what's happening. The angle at the center at your eye or at the observational instrument is being measured on the arc, the segment of an arc segment of a great circle of a sphere.
So where do radians come into play? Is that just another way to confuse us?
Yeah, it is. That's a good point. So radians, I've actually got a, hold on, let me just bring it up.
We got it. I asked the same question when Gav and I first discussed that. I ended up finding a really good video on YouTube describing how radians work.
Yeah, because I've had to do some calculations with them, and it never made sense to me. It's like, why don't you just use the angle? Why do you have to have all these different?
Well, radians is to do with proportions of pi, isn't it?
That's right. Yep, absolutely
Sine,
correct.
cosine, yeah.
Well, proportions of pi is what radians all work out to. It's
So it's based on a ball then, right?
on a circle.
Yeah, looking at all this stuff here, it's just like looking, I think they use the same stuff in geodetic surveying to come up with their different, or their state plane coordinate system.
Well, isn't it true they use star measurements as well in their calculations?
Yeah, what Gavin's been going through on all this different stuff here, that's what I've been thinking about, this is how they've tricked people, surveyors, into believing that they're actually measuring a ball.
Yeah, exactly.
Yep. Exactly the same thing. Yep. And I think you've been attacking it from that same angle as well, Chris, right? You know,
yeah.
And we all know that in all these different things in astronomy and geodetic surveying, where we know they're lying to us because water can't bend, it's that simple, then there has to be a simple way that they've tricked everybody, because we're not all fucking stupid, right?
Yeah.
And it has to have something to do with, or at least from me, my point, it has to be something to do with, we don't quite understand how the eye works and how our mind does not attend to the things properly, and some mathematical sophistry and manipulation of things like spherical geometry and 2 spheres and 3 balls is the way that they've done it. I mean, these are, for me, the kind of major components of the deception. Yeah.
Exactly.
Yeah, that's how they fooled the academics like you. You know, that's how they were able to pull it off.
Yeah,
absolutely.
The common people, it wasn't as hard. They didn't have to. But for people who actually went into the field of study, they had to have a way to actually trick them as well.
One of the interesting aspects that Gab's come up with too is the explanation of how it was actually done, how Gauss and Riemann basically reinstituted Reed's thinking, but changed it to use it in this deception. And it looks like it was deliberate too, doesn't it?
Yeah, I'd say it was deliberate. So Thomas Reed, my favorite guy, right? And I think I've said this before, that, you know, he wasn't just a natural philosopher, he was also a mathematician. So, you know, if I compare him with people like Berkeley or Kant or Hume, then he's got that extra expertise that they don't have. Yeah. And he was the one that basically said, yes, if we think about how our eye works and we define certain things like the horizontal plane, yeah, and how we see straight lines, even though they're curved outwards, but we don't see the curve, then he formulated some very basic axioms of spherical geometry, basically of vision, that are identical to the same ones that Bernhard Riemann, Riemannian geometry, used 70 years later to basically say that we can have a manifold, it's called a manifold now, which does not have to be orientable. So it can be, which is also where the trick is into believing you can be upside down, right? Because that, I think, has to do with the fact that images are inverted on your retina. And there's a big philosophical discussion about that, which we shouldn't go into right now. But the main thing is that Thomas Reed identified that the geometry of vision was spherical geometry, and the same geometry was then used by Bernhard Riemann, who was the protege of Gauss, to basically change the mathematics, or to separate mathematics from physics, in that mathematicians were allowed to think about abstract things like two spheres, whereas physics had to contend with, okay, the mathematicians tell me that, I'll think about the motion of these objects. So they separated position from motion. And in doing that, mathematicians don't know anything about physics. Physics doesn't know anything about the mathematics. And basically what Riemann did, I think, was the geometry of visual perception was misused to bring that deception about and compartmentalize people. Now, yeah. I'm just saying that because you brought it up, Glenn. That's probably a whole topic on itself again, yeah? So,
yeah, I probably shouldn't have brought it in just now. It's just that because you were talking about that actual area, and I thought, yeah, I probably piped up when I shouldn't have.
No, it's okay. I'm kind of asking, should I go further down that line? You know, you guys tell me what interests, right? I don't want to, because we could go on for days.
I mean, I understand what you're saying, but yeah, whatever you want to talk about, Gav. This is awesome.
Then maybe the best thing is just to go into that document that I sent round, and we can maybe just kind of step through it together. Does that make more sense?
Yeah.
Have you finished? Did I interrupt too soon? Or have you finished what you were? You had some things that you wanted to bring up before we went in there. Have you got through all that?
Yeah, I think so. I think the 3 points. So I think, you know, we don't attend to stuff. We'd have to differentiate between tangibles and visibles. And there's also then a difference between tangible geometry and visible geometry. That's the first point. The second point is understanding this two-sphere, three-ball confusion in mathematics, in that these mathematical objects are very, very similar, but you have to understand the distinction between one and the other. One is only the surface, and the other one is a real solid ball of substance. And this one that's only a surface is basically what Riemann did. That's the Riemannian unit sphere that is used, and went on then to be used by Einstein and Minkowski and all these people to talk about, you know, curved space-time. I can't believe I actually believed all that shit, really.
Same here.
Embarrassing. But anyway.
Weren't we? We all believed it, didn't we?
Yeah, absolutely. Yeah.
So if you like, so that was tying into that anyway, Glenn, that, you know, the two-sphere is the Riemannian geometry. But I think what you were wanting to point out was the fact that Thomas Reid discovered this, if you like, 70 years earlier, and very well, I mean, he didn't go into the mathematics in detail. He just put out some axioms up there. But when you look at these axioms and you derive, you know, the next stage of stuff from them, then the equations and the formulas that you come up with are exactly the same as the Riemannian ones. So, and I would think that because Reid has been confined to the dustbin of philosophy and mathematics, I would think that that was very, very intentional. That whatever Reid did, the man was obscured, his work was not studied, nobody went into it any further. And all of a sudden, you know, a couple of years later, they maybe had 50 years to work out how to confuse us all properly, you know? It might be the case. I'm conjecturing a little bit, and I don't want to be conspiratorial necessarily, because we usually never find any resolve if we ask those kind of questions. So, yeah, so maybe let's just dive into that document, or I think that would make sense if I just share my screen again. Yeah, so this was kind of like the basis of one of the first videos I did, and I think in here, maybe we'll just go through this very briefly then, Glenn, before we dive into the other document.
Whatever you reckon, mate. I didn't really know. I was just, because I told you I'd just been starting to read that the book again, and I was sort of thinking to myself, when we go to discuss this, should we actually be discussing the geometry of vision first and then go into your document, or is it better to do your document first and then have a look at the geometry of visibles later?
Yeah. Well, to be honest, I didn't know. I've kind of formulated a little intro, but from then on, I was going to just wing it. Whatever.
Well, no, let's do what you were going to do then. Forget this. Go back to your intro and let's do that document.
Yeah, so the one. Yeah, maybe there's just a couple of things in here that I wanted to point out. So, you know, I talked earlier on about this concept of appearances, and that something is in geometry, anytime we use the word appear, then what we really mean is the angle subtended at the eye by an object of sight. And when I say an object of sight, then I'm talking about visibles. I'm not talking about tangibles, right? And there's actually a couple of experiments you can do that will show you that your vision is spherical. And again, I think we've got a couple of videos on that, Glenn, which we should really maybe just show. But if you have objects up very close to you, then you can actually see the spherical nature of your vision. But if things are kind of like 12 inches away, then the world starts to look very Euclidean again. When it's up close, you can see things appearing to be spherical in certain circumstances. So I think what I want to say there is that if people don't believe that vision is spherical, or that visual perception is spherical geometry, then there are experiments that you can do to prove it to yourself, which I think is highly important. Because me saying that we have a spherical geometry of vision, but you see things Euclidean, is a kind of, for a lot of people, maybe a kind of cop-out, right?
Yep.
So if I was, for example, to draw a spherical triangle in here, and bring this up very close to your eye, so these are three walls that are perpendicular to each other, yeah. But if I bring these things closer to my eye, then the thing will actually start to look spherical. These lines will start to look curved, yeah.
Wow. I'm going to have to do this.
Yeah, there's a scatter of yeah, so
that's
there are two.
One of the things Gav and I have been talking about doing is putting a list together of these little experiments and modeling them, you know, making a couple of videos to show people how to do them.
Yep. Yeah, I think that would be highly relevant to the overall discussion. Yep. Now there's a big question about how the visibles and tangibles actually relate to each other, right? So a visible, and this is the words of Thomas Reid, and you probably heard me saying this in the introduction, we pass from the sign to the thing signified with ease and by natural impulse, but to go backward from the thing signified to the sign is a work of labor and difficulty. Visible figure being intended by nature to be a sign, we pass on immediately to the thing signified and cannot easily return to give any attention to the sign. This is from his famous book. From his famous book, Inquiry into the Human Mind on the Principles of Common Sense. If you ask me, the best book ever written.
Yeah.
I agree.
Wow.
I've actually got it in audio format, and we actually did start doing it as a discussion and a PowerPoint at one stage, but we kept getting dragged off onto other things.
I know, it's such a wide topic, wasn't it?
Yeah.
So a visible and a tangible are both real things. They are both separate mathematical objects of thought, and they are both separate parts of reality that everybody can observe and experience. And a tangible will exist whether you look at it or not. And, you know, if I was up looking down through this telescope and I said to somebody else, come over here and look, they'll see the same visible that I saw. So it doesn't depend on me necessarily. So visibles are are related to the tangible object. It's the tangible object, the light shining from that, that is making this visible exist. And sure, somebody needs to look at it to experience it, and they'll see the visible figure. But if I go away from that, then that object is still shining light, right? And it's only that an eye needs to get in the way to be able to see that visible. So if you like, a visible is a part of the tangible external world that we see, right? That exists out there. And they do have a certain commonality to them. So there's a difference between the geometry of touch and the geometry of vision that should be clearly understood, yeah? And we call these tangibles and we call these visibles. And that comes actually from George Berkeley of Berkeley University, California, the Bishop of Cloyne, who was one of the first guys, at least, who clearly defined the difference between visibles and tangibles. But him and Reid were not of the same opinion. But it's important to understand that sometimes, and this is just a by the by, sometimes tangibles is not the correct word to use, because philosophers sometimes use tangibles to refer to sensations that you have in the body, rather than the way we're using it at the moment to mean physical substance, like, you know, the physical world. But I'm going to stick to the common sense way of thinking about it. So you have visibles and you have tangibles. So if we want to measure tangible substances, then what we're doing is measuring the proportions and the intervals of these physical objects, their shape and their extension, so their shape and size, so to speak, in modern terminology, with respect to each other. So if I'm measuring something, then I'm doing it with a ruler, for example, and I will define a ruler to be, let's say, 1 foot long. And then I will go along the outside of an object with my ruler, and I will say it's 10 rulers long, i.e. it's 10 feet long, if my ruler was 1 foot. So, and when I measure the width of it, of the object, of the physical object, then I'm also doing the same thing. I'm taking my ruler and I'm laying it along. So what I'm doing at the end of the day is I'm measuring the object, or the parts of the object, or the extension of the object, with respect to each other. So I'm relating its width and its breadth and its height using a ruler with respect to each other, with respect to the parts of the object. But when I measure visibles, then I'm always doing it with respect to the eye in a particular situation. The same way I asked you, Zach, what shape the table is. That depends on exactly the relationship between your eye and the table. And we can never forget that that's relative to exactly where you are and how you're looking at it. Also the inclination and the rake of your head and the way you look at things. And that stuff is a completely different way of measuring objects than tangible stuff is. Because one of the differences is, and this is why the geometry of vision is spherical, is that it's two-dimensional. You cannot possibly determine the distance of an object from your eye using geometry alone. You sometimes have depth cues. So for example, you could see that something is further away because you know it's a horse and you know the size of a horse, and you know you can relate to things, or grass that's further away will be lighter than grass that's closer to you. It'll be a darker green closer to you, so that you know that the grass, because it's the same color, if you were right up next to the far away grass, it would be the same color as the grass near to you. But you know that the grass is further away because the color is slightly, how should I say it, diffused or lesser, a lesser intensity of green. But from a purely geometric point of view, you cannot tell whether something is very close to you and very small, or very far away from you and very big. It's called the so-called size, distance, invariance problem. And it's the thing that astronomers have to contend with all the time. They have no way geometrically of knowing whether the star is massive, as they tell us the sun is, and it's 92 million miles away, or whether it's only 3,000 miles away and 32 miles in diameter, or in radius, diameter, or whether it really is the size of a 5-pence coin held at arm's length. You cannot tell the difference in those things from a geometric perspective. And that's why you cannot see the distance of things, but what you can do is see the position of things. And that is the big distinction that we have to make, that yes, with our eyes, we can see the position of certain things in relation to other things, but we cannot ever geometrically, with our eyes, see the true distance of something. Again, I'm ignoring depth cues, as they call them, of which there are a few, but when we look at the night sky, these depth cues are no longer available to us. So that when we look at the night sky, for example, we can't tell geometrically whether that star's far away or not. That's when they have to play with things like light intensity and luminosity and spectrography, spectrography to tell us all these fucking fairy stories, because they can't do it geometrically.
Is there a slight caveat to that with stereoscopic vision for things close, within arm's reach?
Yes, that would be another cue. The fact that our eyes are slightly separated and there is a parallax, if you like, between the two things, then yes, you can, if you like, focus on it. But remember my experiment with 2 toilet rolls? That if you put them together, then all you really see is one circle. So binocular vision obeys the same rules as monocular vision from a geometric standpoint. But the thing to remember is that these 2 geometries and how you measure these 2 geometries are 2 completely different things. One of them, the top one, is our 3D Euclidean world. And the bottom one here is a 2-dimensional sphere, because the position of an object, if that's the only thing that you can find out, the position of the object, and you can't measure the distance from you, then everything appears to be the same distance. So everything appears to be on the inside surface of a sphere. At the same distance from the center point, your eye.
And our eye actually makes that shape. Oh man.
That's another subject where you get into the visual acuity and angular resolution that creates that sphere, the distance that sphere is away from you.
So basically, if I draw the geometrical model now of a sphere with an eye at the center, then this is the kind of, if you like, don't think of this as the eye anymore. Think of this as the geometrical space of visual perception with an eye at the center, looking out. So what you see is basically visible figure on the inside surface of this sphere, the inside concave surface. You're in the middle, you're looking out, and your whole world of visibles, everything you see, every visible object that you see is actually basically being registered as a figure on the inside concave surface of a sphere. So I've talked about this before. The eye is very obviously globular. A few of these things are now in that document, so I'm kind of skipping forward a little bit. So I hope that I've justified to you guys that when I'm looking at how the eye behaves in situations like railway lines or lampposts or things going into the distance, that it is valid for me because the retina is curved and because geometrically speaking, the center of the eye is the place where the rays cross over, they get inverted. So this is where the inversion happens. That's why the the object looks to be upside down on your retina, or in fact it is upside down on your retina, there is a material impression. But these angles here, so this pink angle to the green angle, the proportion of that pink to that green is the same as the proportion of that green to that pink. Nothing is changed. Would you agree with that?
Yeah, absolutely.
Absolutely.
And that these arc segment lengths, because of what I said beforehand, this planar angle and the solid angle from the center of a sphere can be measured by the arc length of a great circle. If I was to continue this, it's a great circle of a sphere. Then we can basically, when we're looking at the phenomena of railway tracks, for example, then we are perfectly justified to use a circle of measure rather than a tangible straight line measurement. So that's why in the document where I've went through the theorems, I can basically use this arc measure to explain what is going on. And I don't need to worry about angles, if you like. Does that make sense?
Yeah.
Yes.
I've got one question, and I don't know whether it's worth. It's about the difference between an angle and a solid angle, a planar angle and a solid angle.
Yeah.
What I know from the definition that you gave, the way you showed us with the pens and the two planes, how it works. But what is the actual? Is it where is there any importance in a difference in that difference?
Well, I think the importance for me is that a solid angle is a real physical substance like a melon. And a planar angle is the angle that we can see when we measure or when we look at a visible object. All we see is the difference between 2 points, right? I mean, I don't actually see an angle. If I'm looking at two stars, then I see that they have some positional separation. But I don't see the line going from my eye to each of these stars. Yeah, all I see is that in my visible, they have a different visible position in my space, and that's what I'm trying to measure. But the very fact that that planar angle that I'm measuring is the same as the solid angle in a real ball is the geometrical connection between the two.
Right. Okay.
Does that help?
Yep, definitely.
Okay. So basically, I feel that, you know, we are justified in using a circle of measure, as they call it. So a complete circle is 360 degrees. The arc segments are in the same proportion to each other as the angles subtended at the eye, and also as the angles subtended then on the retina. They are in proportion to each other. And that allows us to now have a better description of all these phenomena. And one that is basically spherical geometry, the same geometry they use to confuse us.
Actually, when you're measuring those arc segments, are you what do you measure them in?
Well, that's where radians could come in, but then you need to be careful because pi is different on a sphere. That's why I wanted to throw that in. Or you can, in fact, measure the angle, but it all depends on what you define as your visual space and the position of these objects in your visual space. Yeah.
Yeah, but you wouldn't go around and try and measure that in millimeters.
No.
No.
Always in angles.
Yeah.
Yeah.
And this was one of the telling things for me as well, which is why I'm quoting it here again from Thomas Reid, 1750. Right, this guy was a fucking genius. So I ain't a genius, but this guy was. When the geometrician draws a diagram with the most perfect accuracy, when he keeps his eye fixed upon it, and while he goes through a long process of reasoning and demonstrates the relations of the several parts of his figure, he does not consider that the visible figure presented to his eye is only the representative of a tangible figure upon which all his attention is fixed. He does not consider that these two figures have really different properties, and what he demonstrates to be true of the one is not true of the other. It sounds a little bit confusing maybe, but what he's basically saying is, hey, the geometry of visibles is spherical, and the geometry of tangibles, parts, is Euclidean, and that these two things are absolutely different. So that if somebody tries to confuse us by showing us angles using Euclidean plane geometry, but he's talking about some observation, then he's actually not telling us the correct thing, because what he's demonstrating is not true in spherical geometry.
Wow, this was a long time ago, huh? 1750, you said?
Yep. Yep. 1750.
I want to read this book.
Well, you got to read it, Zach. You know, I mean, the man, he doesn't know how to confuse you. It's very simply written.
Actually, Gav and I have had a couple of goes at going through and reading it and discussing, but we keep getting dragged back to our lived life situations, and we haven't finished it yet, but we intend to get around to it, don't we, Gav?
Absolutely, yeah. I think everybody should read that book. It should be compulsory education, if you ask me. And I don't say that lightly, because compulsory is always a bad thing. But in this case, I'll make a fucking exception. Yeah, and I've always kind of said this is the only diagram you will need to know, and it's the one that's in the document, where here's the eye. I've made it whatever 2 units up, and there's 6 units to this whole figure here. So this could be 6 foot, for example, in which case 1 unit is 3 feet, if you want to think about it like that. And the eye's here, so this is a guy that, you know, is standing there, and this is his eye height, and this line here is the eye line. So for me, this is the directly staring out. If you're standing absolutely normal, looking forward, and you haven't got a bend or a crick in your head, you know, you're a normal person, you're looking ahead, then your eye line is going to be this blue line straight out ahead of you. And then I've kind of drawn these objects so that we can talk about lampposts, we can talk about things moving away, we can talk about railway lines. You know, the 2 red things could be 2 parallel railway lines. And this diagram kind of, you know, is available to explain all of these phenomena, why things disappear bottom up and everything. So yeah, I always felt that this was the one diagram that everybody should understand. And then, you know, at least for those people who are not mathematically inclined. Yeah.
Oh, I know. I want to show this to so many people. I've been good though.
Feel free, Zach.
That's perfect, man. I was trying to do that on all my drawings and all my everything I was trying to do. I kept doing it like this though, where the 2 would come together, you know, and I was drawing them on angles. When all I had to do was flatten it out and add that arc, and yeah, amazing.
Gav and I have been having that argument.
Why didn't I do that?
Gav and I have been having that argument since day one, and I was just saying to him the other day that I've come around to realising that it definitely is the other way, is the better way of looking at it. But there's something still egging me back to still figure out what's going back the other direction too.
Yeah, that kind of falls with like the corpuscular rays, anti-corpuscular and corpuscular rays. Kind of works this exact same concept.
Yep.
Well, yeah, if you take that arc and if you were to straighten it out, then all the lines would converge in the center there, on that eye line, radial.
Yep.
Yeah. So it's, wow, that's all they did. They just, I can't believe it.
And I mean, we've been wanting to throw this out for a long time too, but I actually wanted to absolutely make sure that no academic can get against this, right? That's why I was trying to be very careful about making sure that all the argumentation, the mathematical proof, right? That nobody can jump in this after and say, it's a bunch of flat earthers who think they've got the answer with the Dunning-Kruger effect, you know? And that's why me and Glenn have been kind of working on it for at least a year, huh? Is it?
Yep.
Must be at least, Glenn, right?
At least a year. Yeah, I reckon it's coming up to close to 2.
Is it the fuck? Oh, Jesus.
Yeah, it took me about 6 months of looking into angular resolution before I made my first video because I wanted to make sure I knew, when I told people, at this far away, your eye is gonna, at the horizon line, at your eye height, you're gonna be missing this many feet. It's just our eyes can't see it. It's just not there. Our eyes can't resolve that thing that far away.
Yep.
And it made so much sense to me, but I wanted to make sure. I wanted to make sure that what I was reading was accurate. And yeah, because you never know. With the way this was all set up, I'm sure there's plenty of rabbit holes to go down that lead you to making you look like a fool.
Yep. Yeah, and I know they can if they're good at it, right? I mean, I've experienced it firsthand as well. So it was important for me to make sure that there are no holes in the argument, even because I'm not infallible either, right? And I really just don't want to make any mistakes because I know they'll pounce on it and would try and ridicule it. Yeah, so I think we talked briefly about this diagram the last time. I don't know if we want to go through it just to recap.
Yeah, this is the one I've been looking at this in my head all week. And when it the line on the bottom, the red line on the bottom, if it just undulated a little bit with even straight lines, just straight, that little triangles that pop up and then go back down, it would show that that same thing I caught in those pictures. That once the angle is so perfect with the ground from your eye, you just can't see it anymore. It's unresolvable. And it's one of those things that everybody can go out and do, on any road almost.
Yep. Yeah, I think we do need practical examples and practical experiments and observations that everybody can then confirm this stuff for themselves. I don't want to, people shouldn't just believe me. I want this kind of mathematical foundation and then experiments on top so that everybody can say, yep, I understand what the fuck's going on and I can go and prove it to myself, and that's it, game over. As you said earlier, Zach, that should be, hopefully game over.
This in itself, that diagram in itself, straight away puts paid to their ships over the horizon proof. I mean, even if, what am I trying to say? Even if this worked out to be physically wrong and that we did live on a globe, it still doesn't mean that what they put forward is proof, because this is another totally plausible and, from my point of view, way more plausible explanation for that phenomenon.
Well, yeah, this is scientific. This is actually, you can test it. Going to the beach and testing it, I mean, it would change depending on what the weather was like. If you were just using your human eye, that's another thing that I try to bang home so much, is that weather is going to change the amount of things cut off at the bottom. People tell me, oh, that's crazy. How could it affect it? And it goes all back into the angular resolution limit. The more things in the way, the larger that angle is going to get. Yep.
And I think what Glenn was trying to say there, or what he did say, just to recap, was that they have an explanation for why things disappear, why the ship disappears bottom up, and they say it's the globe. But this is a perfectly good explanation and has nothing to do with the fact that we're on a globe. We're on a flat plane and this works. So if there's two explanations for the same thing, and they're equally giving the equal results, then theirs can't be right. Theirs cannot be definitely right if there's a counter explanation. Yeah.
Exactly.
Yeah, it's not a fact if you have another explanation for it.
Yeah, because I'm not now saying this doesn't prove the flatness of the Earth, right? What we're talking about here is how our visual perception works. So we're not proving that it's level in that in a real mathematical sense. Yeah, we're just saying that, hey, now we've got an extra explanation. We have the mathematics to prove it. it's obviously something to do with your eye, which everybody can experience. So your explanation as apparently being the only one that explains the phenomena is wrong.
Yeah.
And that, I think, is, you know, the important part where we need to stick to.
Yeah, absolutely. That it is possible on a flat plane to see all these things that we see. That's where I think a lot of people don't
And
get.
the good thing is, the good thing is it wouldn't happen if I was on a spherical surface, and I agree that I have spherical vision, then you can't have double spherical geometry and have the results. You either have to have planar vision on a sphere, or you have to have spherical vision on a plane.
Yep.
You can't have planar and planar would not give you the results. Spherical and spherical wouldn't give you the results. It has to be one or the other, right?
Yep.
Wow, we need a facility. I think there's one. I bet 500 yards would do it. I bet you could figure some. But it's they study waves. I think it's in Sweden, maybe Norway. But they study waves and the how waves work. But it's a 500-yard long pool with that's totally controlled. If you could control the air in there to all be, you know, pretty much the exact same nitrogen, oxygen based atmosphere, you could prove this without a doubt, you know, empirically, to where they could not. Oh man,
I'm game.
I think you could just about do it on a basketball court.
probably, but I think the further you have, the longer you have, the more visual you could show people. Because I did it on that one floor, it was like 400 feet. And I showed how the bottom of things were getting cut off on a flat surface at just 400 feet away. And then I'd raise up my elevation and I could see everything again.
Yeah.
That's what got me on all this, the whole trying to figure out how that happened.
What I used to call, or Gavin and I used to call the wall of water.
Yeah.
The wall of water, yeah. Explaining that one. But I you know, tell me if I'm wrong, guys, but this diagram, let me just run through it in 5 minutes, the important points, and please tell me if you think everybody can get it, yeah? So this is if you like, a mixture of tangible geometry, because I'm showing 3 lampposts, let's say, or 4 lampposts going on a line, right? They're all the same height, and I'm looking at a cross-sectional view of it, and I would see them all the same height. If I step back far enough away, I know these lampposts are all the same height. That's exactly what I would see, right? Yep. The tangible, these objects. And I've put now our circle of measure in here, so our arc, so that we can see what actually happens. Now, as the top of the lamppost, or I move to the second lamppost, then the position of that second lamppost is going to fall down on the arc from N to O. So it's going to drop in its visible position. And when I say visible position, I do mean that. I don't mean its tangible position. Its tangible position isn't moving. It's fucking nailed into the ground, right? It's not going anywhere. Yeah. Its visible position is dropping in my field of view the further away the top of that lamppost goes, so that I go from N to O, from O to P, and from P to Q. And basically, if I continued, then that's going to drop all the way down to this blue line, i.e. my horizon, yeah? And the ground is going to do the same thing. The bottom of the lamppost is going to start rising to the horizon. The ground rises to the horizon and the sky falls, right? We're all agreed on that. And the very fact that I am now closer to the bottom of the lamppost than I am to the top of the lamppost, if I was exactly in the middle here, if I was at 3 units in the middle between 0 and 6, then both of these things would converge at the same time. And the thing would shrink and smaller, with the same at the top and the same at the bottom. It would shrink and get there. But that only happens if I am in the middle, equidistant between the top and the bottom. If I am not equidistant from the top and the bottom, then other phenomena occur, which is what I've tried to describe in that document. It's not the same. This simplistic way of looking at perspective, that things get smaller in the distance, and it does so proportionally above and below, is only true if you're equidistant from the top and the bottom.
That's actually mentioned by Rowbottom in his original book.
It is, yeah. He explains it as well with straight lines. He doesn't use the arc, which, you know, I think.
No, he doesn't use the arc, but he explains that if they're equidistant, they'll disappear at the same time. They'll converge at the eye line at the same time.
So if I'm just looking at this red line, if I imagine I could see a red line, a roof, and I have a floor, then the roof and the floor are going to converge to my eye line, or to my horizon, if you like, if we want to call it that too.
Which is why boats disappear bottom up, because they convert the, you know, if the sails and everything are higher above your eye line than the hull is, then that bottom section is going to disappear, reach the eye line before the sails.
Yeah, well, actually, it won't reach the eye line. They're going to both reach the eye line at the same time. But what will happen is you will reach the limits of vision, and you will reach the limits of angular diffraction at the bottom quicker.
Yeah. Well, no, they still converge at different times too, don't they? That's what you were just saying.
Yeah, but exactly where they converge at infinity, right? Mathematically spoken, they both converge at infinity. But the one at the bottom will reach the limits of vision and the limits of angular diffraction quicker.
I gotcha.
I think it's an important distinction to make, because I don't believe in infinity anyway. I'd rather see indefinite. So you have a finite length and you have an indefinite length. I hate that word infinity, because it's just a mathematical trickery.
Is that sort of why you can't draw this diagram to its full extent?
Yes.
Because that convergent points is just too far in the distance, too far to the right.
Yep. Yeah, you would have to be so far away to take it all in one view that you wouldn't be able to distinguish it anymore.
Yeah.
If you like. So again, we reach our limits. But just to go through the argumentation, so when you look at the horizontal spacing between two things, then if I go from H to A, then the horizontal spacing is moving from U to T. And when I go from here, from A to C, it's going from T to S. And when I go from C to F, it's then going from S to R. Those are the 4 points that I have there. And this angle here between S and R, if you can imagine that this angle here, the difference between these 2 points is going to be, when I go further away, so small as to be insensible. And that's when the limits of vision are reached. And when that happens, and it's probably due to the fact that we only have a certain amount of rods and cones on the back of our retina, that we can make that differentiation. But basically that angle is so small that we cannot longer differentiate between these 2 points, you know, from our eye limitation. And that's when this whole horizontal space disappears from view. And anything sitting in that horizontal space also disappears from view, because you can't tell one point from another. And if you go even further to the right, then the same principle kicks in with angular diffraction, the Rayleigh criteria, which basically says that 2 light points can't be distinguished from each other. So you have the vision limits of the eye, and at some point you have the visual limits of nature. And when that happens, those points are no longer distinguishable. Anything in this interval is then lost to sight because it's no longer distinguishable. You cannot see it anymore. And you can see from the top half that the angle's still a lot bigger, right? So this angle has not reached that limit the same way the bottom part has reached the limit. The bottom is always going to reach that limit sooner because you're closer to the ground, or closer to the bottom of the object in this case.
That's why the sun looks like it sets.
Yep.
And why the gaps between, what do they call on the railway lines?
The railway lines, yep.
The gaps between the, what are they called?
The tracks, railway tracks, right?
No, not the tracks, the things that the tracks are on.
The ties, a railway tie.
Yeah, yeah. Why you can't, like when you're close, you can see the spaces between them. You can see the ballast, the stones between them. And as they get further away, you get to the point where you can no longer see the ballast.
Yep. And one thing about the railway tracks that I think is important as well, that I'm just drawing a sphere here very quickly. So I know you all know what a sphere looks like, but a visual aid does help. You can see that at the North Pole, these two lines converge, and at the so-called South Pole, they also converge, right?
Yep.
In spherical geometry, these two lines are supposed to be parallel to each other, and they converge, right? That's in the definition of the spherical geometry.
Yep.
Now, if I'm on a railway track and I look forward, then I will see the railway tracks converge to a point. And this is the important part. If I now turn 180 degrees and look the other way down the railway track, they're also going to converge to a point.
Yeah, they don't go spread out the other way.
They don't spread out, right? So basically what I'm saying is that that's also a very clear indication that it's spherical geometry we're working with, because only spherical geometry can do that. Converge in front of you and converge behind of you, like the North Pole and the South Pole do. So your vision, that's another example of, you know, I'm not saying it's a proof, it's an observational experience that shows you that these axioms of visual geometry are spherical and that they are self-evident and that you can observe and experience them yourself.
Well, it's an evidence, I reckon it is a proof. It's an evidence that your vision is spherical.
For me, it is too.
Because you do know those lines are parallel.
Yes, I could walk down that railway track and I know they're not getting smaller. And the further I go, they're still going to converge. Yep. So it's, in that respect, it's just like spherical geometry is. Yeah.
Excellent explanation. Just had a good aha moment there.
Yeah.
Let me just skip through this document, because I think this basically takes us through the document of the theorems that that are in that document. But I'm pretty sure I had some examples, to try and make this a little bit more, how should I say, easier for people to. So, explaining why lampposts, I've just put lampposts in there, and, I've tried to explain it a little bit more. It can be the same thing as a railway, what I just talked about. Yeah.
Yep.
It's the same reason buildings disappear from the bottom up. Same principle. Or the sunset. Yeah. Or a brick wall, if you look at a brick wall or a corridor.
Now, if I was thinking, if you had a long corridor like that and you put your head up against one wall all the way to one side and something down at the far end against the same wall, wouldn't that one side of it that's near the wall be cut off? Like
this picture here? A
bit
like this one? Like you will not see the pictures on the wall, these pictures that you have on the wall. You will lose sight of them quicker if you're closer to this side than you would of the pictures on the other side of the wall.
Yeah.
That's what you mean, right?
Yeah, absolutely.
Yep.
Give them for everything. Yeah, great. Wow.
And I actually did a whole modeling of how a corridor looks, so that, I can move the corridor wall backwards and forwards and show what's actually happening on the eye. And I hope you guys can see this a little bit, because this is where you can see that if you can now think of this as the eye, or you can think of it as your geometrical visual space, it doesn't really matter. Thinking of it as the eye is maybe easier for most people and not that abstract geometrical thing. But basically, as this wall moves further away from you, and when I say wall, I'm basically taking a snapshot of a corridor, let's say here, at where these two doors are, and I'm taking another snapshot further down the corridor, and another snapshot, another snapshot. This is what this plane represents here. And if I move that away, then what's happening on the eye, this red, what looks like a rectangle, is going to look more and more like a Euclidean rectangle. You will not be able to see that it's actually curved. You can see, because this is fairly close to you, that there is still a little curve on these lines, right?
Yeah, like
And
the
if it,
example you showed of putting something close to your eye and it looks spherical, and then
that's right. So if
That
I was to
still
move
blows
this
my mind.
very close to my eye, then this rectangle will blow up and fill basically all of my eye here, and it will be very obviously spherical. But as soon as things get further away from you, then there is hardly any difference between you seeing it Euclidean and it being Euclidean. You will not be able to tell the difference, at least not from your, your eyesight. And that's, when I said, when I say spherical and people say, but Gavin, I don't see a curve, then that's what I was trying to explain. You don't see the curve because it's a very good approximation to the Euclidean world at normal distances of sight. And especially far away, you can't tell the difference. You can only tell the difference when it's really up close.
Yeah, really up close. I
Well,
couldn't
actually,
believe how much it curves.
if you go back a bit, Gav,
Yep.
you can see there's that diagram in the bottom right compared to the one in the bottom left.
Yeah.
Oh, that's right. Yeah,
Much
that is it.
more curve.
You can see it's curved, so that the plane's right up against to the eye, and you can see that what's being left on the eye, the material impression on the retina, is actually curved. Yeah, and it's only then that you could really see it. So I'm here only 1.5 away from the guy, and here I'm at 4.3. Yeah.
It's good to see this one. I've been lucky enough to see this one in animation.
I can do that right now. Hold on. I'll just open it up. So you can see I basically modeled a corridor here with roofs and stuff like that, I modeled a sphere for the eye. I modeled the horizon, the azimuthal, or what do we call them? The longitude circles and latitude circles. I made various lines and walls and planes and spheres. So, but basically, if I zoom out a little bit, hopefully you guys can see the overall picture.
Yeah.
So I can now move this closer to the eye, and if I now zoom in a little bit more, then you guys can see that the thing is curved. If I turn it around a bit, yeah, then that's the picture I was basically showing. Yeah. And if I zoom out a little bit more again, and move the wall or the placing plane away down the corridor, and now zoom into this part, then you can see that it's, indistinguishable from a rectangle now.
Yeah.
Yeah.
They look parallel.
And I've modeled, all these different things as arc measures, right? And you can see the angle here in the middle of this sphere is that solid angle I'm talking about. Mm-hmm. So, I can basically show what these angles are in all the different parts, yeah? And yeah, the main thing here was that I basically, hold on, if I can get rid of a few of these things, then I can show you guys in a little bit more detail. Or maybe I'll prepare the next time we come on and we can go through the build up of how I built the eye, or how I built the geometry of visual space. I basically just built it with 3 equatorial circles. So this one, the green one, there's a blue one going like that, and there's a red one going like that. And I basically call them, let me just stop this share. I call them the horizon circle. So the circle that goes around, this idea of a hula hoop around me. I call it this one, which is the big circle that goes over my head. And that's the thing that tells me what is straight ahead. And the other one is what I call the facing circle. So the one that is, if you like, if I face something, then I have that. If you like, if you imagine there's a circle drawn, there is a circle drawn on it. So, so that's my facing circle. This is my horizontal circle, and this is my, circle. So the eye is made up, if you like, of these three great circles that I've drawn on a sphere. And when I look at something and I elevate things, then I can use the angles between these three great circles to make those measurements and show these arc segments.
Wonderful.
They look like they were originally based on the Cartesian.
How long did that take you to do that?
Oh, I got into the swing of things one day, and I think it was like more or less in one day. I just got up in the morning and I thought, you're going to fucking finish this. But I had been playing with GeoGebra for quite a while, so I've got quite a whole bunch of GeoGebra stuff that, you know, I think it's a pretty cool program for mathematicians just to, you know.
It's like experimenting almost, pretty much. Mathematical experimentation.
I did my first copy of a Gav diagram just the day before. Yesterday, I think.
Sorry about that. I was up late.
Me too.
No problem. Yeah, so the other thing would be, I don't know if you guys want to still go through that document and understand some of the subtleties of it, but, you know, or read it in your own good time and come back with questions. You know, I think for me, it's important everybody gets the overall picture of, you know, of the high level overview, and what's in that document is very particular things about, depending on where the eye is relative to certain things, what we can and what we cannot see. And I just wanted to prove it all geometrically as well, so that there would be no comeback and, you know, there's no idiots saying, you know, there's a mistake in here, the whole thing's wrong, right? So that's where I really wanted to be, how should I say, very grounded or fundamental in my approach, so to speak.
Yeah, I haven't found any yet. I'm gonna go over it again a couple more times. I've been reading it at work on breaks.
Yeah,
that's my new break time thing. I'll go out there and I'll start. And I've started it over about 3 times now. Because whenever I start going through it, I'll get to a certain point, and then it's like, well, I need to go back and. But I've read it twice now at home, and it's. I haven't found anything wrong yet.
No, it seems pretty right to me. I actually was just telling Gav, I went in and got into GeoGebra because there was a couple of things I wanted to prove myself, and I did prove them to myself. They were, you know, they weren't intuitive. That's why I put that little post in yesterday, Gav, where you said that some are occulted, some of it's intuitive, some of it's not. But,
no, there's some subtleties in there that are again, you know, very much, and maybe just to explain that once more. So I think that perspective is, for me, the mathematical rules where I can take a 3D object and apply mathematical rules to show a representation on a plane. Usually with a window of perspective, you know, the veil, the window that they used, the old perspective painters, Great the way that word window crops up in all our computing language nowadays. And I think there's a distinction to be made between that and what I would call the theory of natural perspective, where I'm talking more about geometrical optics, how the eye works, and that there has to be, you know, a distinction between these two, which they really like to fudge nowadays, right? You know, they'll talk about lenses and other, you know, they'll show you these optical experiments where they show you a little candle there and they point and you've got some rules to show it inverted. So they talk about those things in a very simplistic manner, and perspective is also simplified down to, kind of, you know, general things that everybody should know. Oh yeah, double the distance, half the size. Not true. Not fucking true, right?
Bullshit.
And there's you have to distinguish between how vision works and how perspective goes. You know, I think that's immensely important.
If you had a building, I don't think the distance would make any difference. But if you were on the 34th floor of a building, and that floor was exactly 1,000 feet above sea level, and you had another building 100 miles away, or within, even 100 miles away, that was still the same floor, was at the same level, same distance above sea level, they would still be on your eye line. That line would not change altitude. The only things that would change are the distances of things below and above, depending on, like if you had 30 floors below and 70 floors above on both buildings, you'd see things converge at different rates.
Mm-hmm. Oh, that's a great experiment.
There's another thing here that might be quite interesting for you guys. When does a circle appear as a circle? Which I don't know if you've heard the Glober argument that if you're looking at a clock on the wall, right, and you go to one side of the clock, then the clock will appear to be an ellipse. And Globers will always say it can't work in a flat plane. If the sun is a circle and it's going round, then it should change its shape, right?
Right.
Yeah.
And, intuitively, yeah, they're kind of correct, right? You can look at a circle on a wall, and if I move to the side of it, then it will look elliptical. But there's actually a few things that, again, very subtle in there. And I found an old English translation of Euclid's Optics. So Euclid did not only just do the elements of geometry, Euclidean plane geometry, he also wrote a pamphlet about optics. And the very first English translation ever made was in 1950. You got to believe that, right? I mean, it's amazing, right? Mm-hmm. And in this translation of Euclid Optics into English, he's got some theorems in there that describe how a circle appears. So I went through this paper. This is the original proof from Euclid, right? In blue. And I then basically remodeled them in GeoGebra. So let me just go down to it here. And basically what he's saying is that if you've got a circle here, I'm just drawing the circle now on the ground, and I'm directly above the circle, directly above the center of the circle, sorry, at any altitude, then when I look down at that circle, it always is going to appear to be a circle. It'll get smaller, but the higher I go, or the lower I come down, it's always going to be a circle. The reason for that is that the angle subtended at this point, the angle subtended at the eye, if that's where my eye is always going to be equidistant to any of these two side points or any of these 2 points. So any diameter will appear to be the same ratio. And if two diameters are the same, then it must be a circle. If two diameters are not the same, then it's an ellipse, right? So that one is very clear, that if I am straight over the center of a circle, or I'm facing, maybe a circle's drawn in a wall and my eye is directly opposite the center, then I can move back or move forward. It's always going to look like a circle to me. Agreed?
Agreed.
Yep.
But there's also another one where everything will look as a circle to me. Again, this is the Euclidean original proof, right? And I modeled it in GeoGebra again. And basically, it's the special case where this radius of the circle, so this from E to B, the distance you are away is the same as the radius. So in the first one, it didn't matter how far I went away from the circle, it would always appear as a circle, just get smaller or bigger. And in this case, it's that I am exactly at that position away from the circle that is also the radius of the circle. It's a special case, right? And if that's the case, then basically using Thales' theorem, you know that that is always going to be a 90-degree angle. It doesn't matter where you are. And basically what it means is that if you are anywhere on a sphere that is the same radius as the circle you're looking at, so the circle I'm looking at is this green one, the eye is on the surface of a sphere. It doesn't matter where I go in this sphere, this thing is always going to appear as a circle to me.
Yeah.
So why does the sun always appear to be a circle?
Because of
Again, we're back to the
eye,
spherical geometry and the way the
spherical
eye works.
geometry of the eye. Wow. Yeah, because with our limit of how far we can see and everything like that, it's not like we're seeing it, shrink away and go off into the distance. There has to be special circumstances. You have to be high up on a mountain where you're elevated and not so close to the ground. So this makes so much sense. So it's always pretty much about the same distance away from us.
Yep.
The way we're seeing it.
The way we're seeing it is basically all the same way. And if we agree that the circle diameter of the sun, if this is the sun I'm looking at, right? The green one, and it's 32 miles, then it means that it's 16 miles is the radius basically of the sphere. And if I'm anywhere on that sphere, then that will always appear to be a circle, because the distance from here to here, or the distance from there to there, is always going to be the same. And the way that you know something is a circle is if two diameters are of equal proportion in a one-to-one relationship. A condition where a circle always appears as a circle. And that's when the enclosing angles are the same. And basically this is Euclid again. I've just modernized it, so it's not coming from me, but what this guy was saying, that the enclosing angles, as long as they're the same, then it also looks like a circle. So here it is. If that's where my eye is and I'm looking at this circle on the ground, but you could just transpose the whole thing, right? I could be on the ground and the circle could be in the sky. Mm-hmm. So, geometrically it doesn't matter. Then this thing will look like a circle when the enclosing angles next to each other are equal. So it doesn't have to be directly above. That was case number one. It doesn't have to be on a sphere. That was case number two. There is also the special case, where when the enclosing angles are the same, it will also look like a circle as well. So I was just trying to find out, what the hell does that mean? Why is it that we see a circle as a circle? And there's a lot of information in here that I don't think I should go into right now.
No, it looks like a fascinating read, though.
It is.
Yep. I'll send it to you guys too.
So when did he write this? How old is Euclid?
So Euclid must have been, they reckon it's 1,500 to 2,000 years ago.
Wow.
And the only translation, and it says on the actual translation that this is the very first one. The very first English translation of Euclid Optics was in 1950. I could hardly believe it when I heard it. Why?
Yeah, why? They're hiding something for...
I don't do Latin and I don't do fucking Greek, so, why? And I don't do Arabic. These are the three other languages, right? And nobody bothered to translate it into English until 1950?
Yeah, talk about trying to hide something and keep it under wraps.
There's no doubt in my mind that's what was going on.
Yeah, mine neither.
Yeah, all this should be taught to you when you're in school.
One of the arguments that they always have is that they say that Polaris, a sighting of Polaris, whatever degrees Polaris is sighted at, is proof that we're on a sphere, because on a flat plane it apparently wouldn't work. So the globe argument is that the light rays come from Polaris. We are all on a globe, and if anybody takes a sighting, then it will correspond exactly to your latitude on a sphere. Yeah, you've heard that argument, right?
Yeah. Oh yeah.
And the proof that it doesn't work on a flat plane is this one, where they say it would only work at two specific points, namely if you're directly below Polaris or you're at 45 degrees. Everything else wouldn't work. It would all be wrong. Yeah. So, but if you look at it basically from another point of view, namely this one. So this is the whole thing that I modeled then in GeoGebra, which is basically, again, showing their argument first. So this one's kind of showing, there's my latitude at 45 degrees. I'm on that circle of latitude, and I'm observing Polaris, then it would be a 45-degree angle. That would be correct for basically any latitude. I've given 2 examples here of 52 and 18. But the other way to look at it is that if I do an orthographic projection of that latitude down onto a flat planar equatorial circle here, then that's that blue line here in the middle. If Polaris, the more if 0 is the North Pole, if we take, if you like, similar to the azimuthal, so that latitude is actually the distance from the center, and longitude remains the direction around the circle, then it actually works out to be exactly the same. That the further I go from the center point, we know that Polaris drops visibly in the sky, yeah? So that if you basically think of latitude and longitude as being the distance outward from a North Pole center rather than circles on a sphere, then it's absolutely perfect. Basically, our perspective vision is the answer why it works. You remember this, Glenn?
The glasses.
This is a picture of, just something very close to me, and I was just playing with the various things. So I'm stood basically here on this white line, and I took a picture of what I saw, or what the camera saw, and then I was just looking, to demonstrate what we mean when we say we don't attend to visible figure, right? So if I take away this image, then all the visible figures of the things that we are seeing are actually like that, and not, when we look at the object or we look at the scene like this, then we don't notice all these things, right?
No, because we know that they're all the same size, and they're we apply it in our brain that they're like that. We don't see it like this.
Exactly. We actually do see it like that. We just don't attend to it.
Yeah, we don't attend to it. That's what I meant to say.
It's the attending to that doesn't occur. We don't occur. We don't attend to that. Well, that is there, the tangible view. Take the photo away, and you've got the visible view. That's the visible. That's the visible world. And I think that's the point to make there, Gab, is that there are those 2 worlds.
Yep.
That the visible world is a world of itself.
Yes. But it's obviously related to the physical world, yeah? I mean, they can't be there if the physical world wasn't there, and there wasn't an eye to see it. And I like this diagram because it demonstrates quite a lot of the things. So if you start to look at the shadows here between lines, or the sizes of these lines, then you can see, for example, just to take one example, these slats here are all equally spaced, and they're all the same size. So this guy who built this fence made probably one section like this. He nailed the slats down, and then he had a template, and he copied it, and he copied it. And there's 1, 2, 3, 4, 5, 6, I don't know, 8, 10 sections until you reach this tree up here. Now, that means that the spacing of all these things is the same. And I mean, I've looked at it. I mean, it's accurate at least to, a couple of millimeters. I'm not saying the guy did it, industrial strength, but it's a fairly accurate fence, right? Built using, typical Euclidean planar tools. He will have had a level and a ruler and various things like that, right? So
he probably would have used a jig.
Okay, yep, point taken. The main thing here, though, that if you see, for example, the shadow that this slat is leaving on the ground, then the length of this shadow is obviously getting smaller and smaller and smaller and smaller and smaller and smaller. And the point that I was making about the horizontal spacing, so between this shadow and this shadow, is getting less and less and less. and less and less and less. And back here, I can no longer see the horizontal spacing between the slats. Yeah. So if there was a little bird sitting between those slats here and a little bird sitting between the slats down there, I'd be able to see this bird, but I wouldn't be able to see the bird down there because anything between that horizontal spacing will be lost to sight.
Yeah, this is a great picture. This is fabulous, the way you put it all together like that. Everybody needs to see this.
Yep, so this would be a typical diagram that anybody, I mean, that's the beautiful thing about this, you know, you can go out into nature and just take a picture of a fence or a barn or any scene, and you can basically prove to yourself what I'm saying in that document, that as things get, you know, further away, the horizontal spacing, you reach the limits, parallel lines converge, stuff in between can't be seen. If I was to drop my eye down to the level of the ground, so if I put my camera at the level of the ground, then we would again have noticed these things disappearing bottom up. What you suggested, Zach, that, you know, we do these kind of experiments, but basically anybody can do them in the quiet of their own, you know, their own home, so to speak. Yeah. To prove to themselves that what I've written in that document is correct. At least I hope so.
Yeah. Yeah, I think you are. I mean, it's not, I don't know, it's really not up, one of those things, it's not for debate. You're just stating obvious things that anybody can go out and see empirically. We can all go out and see this written.
The sophists will definitely try to debate it.
Yeah, yeah. But I mean, it's like you said, when you get your mindset into actually differentiating those two worlds and then looking at them both at the same time.
Yep.
But with that mindset, it helps so much. It makes it so much clearer.
Yeah.
Yeah. So it's just to try and put it all onto one big. The top kind of explains, you know, the physical world and we're looking at it and natural observations. The second one shows this visible figure and extension that we talked about. That's the way we see things. Parallel lines meet at 2 points. Every right line is an arc segment of a greater circle. You know, circles always appear as circles if you're at the center of a sphere. And if you look at a circle, it's always a circle. It never changes to an ellipse. And then on the right-hand side, the deception, if you like, that they're always telling us it's planar representations is all we get. So they miss out the middle bit. The middle bit, if you like, the signs are the things that they don't want to tell you about. And they basically go from the left-hand side to the right-hand side and skip the bit in the middle. And then, yeah, there's also something called astral geometry, which is where planar and cylindrical geometry have their commonality with spherical geometry, because all of them are basically 2D planar. Obviously, cylindrical has an altitude, but the planar part and the spherical part, so the bottom of a cylinder is basically the latitude and the longitude. Instead of it being on a sphere, you can do it on a plane, as Glenn quite correctly pointed out earlier on. He is further out than we are, and I'm in the middle, and you guys are probably closer to the center, right?
Yep.
And that's actually also a definition of latitude. It doesn't have to be a latitude circle in a sphere. And that's where spherical and planar geometry, you know, have their commonalities, because to make it spherical is just this mathematical trick of curving the surface into a space that you're not allowed to think about.
And that's exactly how they transferred their so-called spherical ball in geodetic surveying. They wrap the cylinder around it and put all their information onto that, and then roll it out onto their state plane coordinate system.
Yep, that sounds exactly right. Because remember, I told you that's also cylindrical coordinates is what air traffic controllers use. So each air traffic control tower is in the center of a cylinder, and that's the space that they control. And they look at the world as, you know, being going outwards from their point in the middle of the cylinder, and then the altitude of the plane is the column above. And basically a plane jumps from one cylinder to another in the control of each of these air traffic controllers when they're moving, you know, across the earth. So the whole of air traffic control is done using cylindrical coordinates. Again, you know, another pointer to how the whole thing, you know, fits together. Yeah. We have been convinced that we live on a spherical world which we see through Euclidean eyes. But the truth is, we live in a Euclidean world which we see through spherical eyes. Yep.
That's perfect.